Alrighty, good morning everybody, and welcome back to Calc 3. Plan for today is we're going to finish off Standard 16 by working through one more example, and then we're going to jump into Standard 17, our final standard of the semester. Yay. And which we'll start looking at vector fields. Usual office hours over the next few days, Standard 16 quiz on Wednesday. So here's what a sneak peek of the rest of the semester looks like. Wednesday, we're going to do Standard 16 quiz and finish discussing Standard 17. Friday, Standard 17 quiz. And then a day of, you get to just come and ask questions, and we can talk about whatever you all want to on Friday after the quiz. Monday, last day of classes. Exam 4. Which will be like the final exam that will cover every single standard. And then you'll have, of course, the final exam. So, 2 exams left, both of which will be over every standard. Those will kind of be your last chances to get masteries. I encourage you to use them wisely. Any questions or comments before we get started for today? Yes, Sarah.
Let's see. This is a question about the final. Let's say that somebody, let's say I take the quiz on Friday on Standard 17, don't do so hot on it, so I don't have a mastery, and then I take Exam 4. And I still don't do so hot on it, so I still don't have either mastery. Will there be 2 opportunities to get a mastery in this section of the final, or will it just be 1?
There will only be 1 opportunity to get a mastery on the final. However, I will still give you a retest next week and the following week. So in that scenario, I would encourage you to do a retest on Standard 17.
I know you said before, like you only can have 1 retest a week. But like, if I've missed a couple, is there anything you could possibly do?
Send me an email about it. We'll see.
Will the final have the same thing with front and back, 1 sheet of notes as all the other exams, or is that?
No, it will not.
Okay.
2 sheets of notes, front and back. Whatever you want written. And you know what? I'll let you have 2 sheets for exam 4 as well. Why not? I need to remember that I said this and tell it to the other class. Any other questions or comments? While we're talking about the final, I will mention one thing. I forget when your final. I'll talk about Wednesday. Basically, I'll tell this on Wednesday once I've looked up the exam days. But if you want to take the final exam with the other class, I will allow this. Just send me an email by the end of this week letting me know this. Not offhand. I'm going to look this up and tell you on Wednesday.
So you mean we can take that final exam instead and not in addition?
Instead, not in addition, no. You're not allowed to take 2 finals. Dr. Gerstle already has enough to grade. Oh, yeah, grading. Sorry, I didn't get the Standard 15s graded over the weekend. I'll have those back to you on Wednesday. And once I do, I'll update Blackboard and send you an email once that's done, and I'm guessing that'll be done tomorrow morning/afternoon. In that case, a mathematician one day decides that he is sick of math. What a terrible mathematician. And he tells the fire chief he wants to be a fireman. Fire chief says to him, "Hey, you seem like a good guy. You're a mathematician after all. I'd be glad to hire you. But first I gotta give you a little test." So the fire chief takes the mathematician to the alley behind the fire department, which contains a dumpster, a spigot, and a hose. The chief says, "Alright, hypothetical situation. Suppose you walk into the alley and the dumpster is on fire. What do you do?" Mathematician thinks about it for a second and then says, "Well, I'll connect the hose to the spigot, turn the water on, and put out the fire." Chief says, yeah, good job, that's great. Now, what would you do if you're walking down the alley and you see that the dumpster is not on fire? Mathematician has to think about that one for a minute. And finally says, I guess in that case I would start by lighting the dumpster on fire. Chief yells, "What? That's terrible. Why would you light the dumpster on fire?" Mathematician replies, Well, that way I reduce the problem to one I've already solved. Well, you shouldn't be careful around mathematicians and fires. Okay, so I wanted to let me try to hit record. Okay. I wanted to do one more example from kind of the end of Standard 16, just to have you another example in your notes to look at in preparation for the quiz this Wednesday. And what I would like to do is I would like to do the integral with which I introduced Standard 16. The integral of square root of x squared plus y squared plus 1, where x goes from 0 to 2, and y is going to go from 0 to the square root of 4 minus x squared. So we said at the start of Standard 16 that we can't really integrate this directly by just integrating this nicely with respect to y, unless we want to do a trig sub. And we can't really do the trick where you swap the order of integration and start by integrating with respect to x either, because that wouldn't actually really be any easier. So now that we have Standard 16 to draw on, what would be another approach that we could take in trying to evaluate this integral? Stop. Yeah. So to me, this looks like something where we can convert to polar coordinates, and it might be helpful, mainly because I think x squared plus y squared is something that we could convert to polar coordinates without too much hassle. Specifically, what do we know that x squared plus y squared has to be equal to in polar coordinates? Not necessarily, only if we're specifically looking at over the unit circle, but just in terms of r and or theta, okay?
R squared.
It's going to have to be equal to r squared, which if you're looking at a circle of radius 1 where r equals 1, then yes, that would be 1. But in general, does not have to be, doesn't look like it's going to be the case over the set we're integrating. So I think we're going to be able to integrate instead square root of r squared plus 1. And let's rewrite the set we're integrating over in terms of polar coordinates. I have a set of points, x, y currently, where x goes from 0 to 2, and y is going to go from 0 up to square root of 4 minus x squared, which if we graph out, let's see. 0 goes to square root of 4 minus x squared. It's going to look like this. And if x goes only from 0 up to 2, it looks to me like this is going to be the set that we're integrating over. Kind of the inside of this disk with radius 2, the top right corner of the disk, centered at the origin. And the question is, how can we rewrite this set to be in terms of r and theta instead of x and y? Jackson?
Theta goes from 0 to pi halves.
Yeah, looks like theta is going to go from 0 to pi over 2, since all the points we're looking at are in the first quadrant. We're only looking at points where the angle created with the positive x-axis here is less than pi over 2. And how about r in this scenario? Right? I agree. It's to me like r is going to go from 0 up to 2. Because we're looking at all points in the first quadrant whose distance from the origin is less than or equal to 2 units. So when we swap out our xy integral in terms of polar coordinates, we're going to let r go from 0 up to 2 and theta is going to go from 0 to pi over 2. So that when we do all of our substitutions, we're going to get an integral from, as theta goes from 0 to pi over 2, of the integral as r goes from 0 to 2, of square root of r squared plus 1.
Shouldn't it also have an R for multiplying by the decoding?
Indeed. Keeping in mind that when we switch from xy coordinates to r theta coordinates, we need to multiply by the Jacobian of the transformation, which, as we saw last Friday, means that we just need to multiply by a factor of r, and going from xy coordinates to r theta coordinates. So we end up having to integrate r times square root of r squared plus 1. How can we integrate that with respect to r? Melanie? Okay, what would you want u to be?
R squared.
Let u be r squared? Jackson, is that what you're going to suggest?
Yep.
I like the sound of that. I'm going to do one thing that'll make our life a little bit easier. I'm going to let u be r squared plus 1, just so everything inside the square root can come up, can be our u term. But then, yeah, I think this is going to work out nicely. If we take our du dr, we'll get 2r, which means du is going to give us a 2r dr. Right now, we don't have a 2r dr, we just have a single r times dr term. So if du is equal to 2r dr, what's going to be equal to just a single r dr? Oh.
1/2 du.
Just divide both sides by 2. Replace r and dr with 1/2 du. And when we do that, we will end up with an integral as theta goes from 0 to pi over 2. Integral as r goes from 0 to 2 of 1/2 square root of u du d theta. Right? Where the theta integral stays the same on the outside, that doesn't change, but our r integral is going to become a u integral in order to help us integrate here. So I think now we can go ahead and integrate with respect to u. 1/2, we need to integrate 1/2 square root of u, which is 1/2 u to the 1/2 with respect to u. Oh, let's see. How would we integrate 1/2 u to the 1/2 power with respect to u? I don't think we're going to have u to the 1 power. If we add 1 to the exponent, what would we get?
3/2.
Yeah, so we're going to have u to the 3/2 times what? Quite. Yeah, we'll leave the 1/2 out in front for now. So we take u to the 3/2 and then divide by the new exponent. What's the same as dividing by 3/2? We take the reciprocal. It's going to be 2/3. We're going to get 1/2 times 2/3 u to the 3/2, which I'm just going to go ahead and simplify down to 1/3 u to the 3/2, evaluated from r equals 0 to r equals 2, and then, of course, we'll still have a d theta term. Sorry, Matt, I'll pick on you a little bit. That was a bit of a messy one. What do we need to do before we start plugging in 0 and 2 into this expression? What?
substitute r squared plus 1 back in for you.
Yeah, we're going to resubstitute r squared plus 1 in for u. By the way, Emily, the reason why I wanted u to be r squared plus 1 is I just wanted a square root of u term rather than square root of u plus 1 term here. It wouldn't have really changed very much, but maybe integration, I think, of that term is a little bit easier. So that's going to give us 1/3 times r squared plus 1 to the 3/2. I'm just going to go ahead and write that as square root of r squared plus 1 quantity cubed. Because taking something to the 3/2 power is the same as cubing, and then taking the square root. Now we can plug in 0 and 2 into this. We'll get 1/3 square root of 2 squared plus 1 quantity cubed minus 1/3 square root of 0 squared plus 1 quantity cubed. Let's see, 2 squared plus 1 is 5. 5 to the 3/2 is going to be 5 square root of 5. This will be 5 square root of 5 over 3. Bennu, what would you get if we took 0 squared plus 1 cubed square root of that?
Just 1.
Yeah, 0 squared plus 1 is 1, 1 cubed is 1, square root of 1 is 1. And then this will give us a minus 1/3. So we did a u sub in order to do our initial r integral. We still have to integrate with respect to theta. Any questions or comments so far? Don't need this anymore. Let's see. Olivia, what would we get if we integrated 5 root 5 over 3 minus 1/3 with respect to theta?
5 root 5 over 3 theta minus 1/3 theta.
That's just a big constant term. Just need to multiply this constant term by theta to when we integrate. So that'll give us 5 root 5. I'm just going to combine it into a single fraction. 5 root 5 minus 1 all over 3 times theta, where theta is evaluated from 0 to pi over 2, which is going to give us 5 root 5 minus 1 all over 3 times pi over 2, and then minus a term that'll just become 0 because we're going to multiply it by 0. And then I believe our final answer will be 5 pi root 5 minus pi all over 6. Not a particularly nice number in the end. But where this came from was taking this initial integral, which we couldn't integrate as is. We also couldn't just swap the order of integration to integrate it. So we converted it to polar coordinates by kind of looking at what's the set of points and how can we write that with r's and thetas instead of x's and y's. Then when we got to this point, we could do a u substitution to help us integrate with respect to r, which got us to here. And then when we integrated with respect to theta, we just ended up with this expression in the end. Questions, comments, or concerns? All right, gonna do it then for standard 16. Brace yourselves. It's time for the final packet of the semester. So I thought for our last standard of the semester, we would look at a kind of a different topic, different from integration, called vector fields, where there's a lot you can do with vector fields. Since we're only going to spend a couple of classes looking at them, I wanted to focus on a little bit of the highlights, including how differential equations can pop up and make for an interesting sort of problem if you're trying to look for, say, help, I'm driving a boat and it's trapped in a whirlpool, how do I get out, sort of way. Because, let's face it, that's happened to all of us before, right? So here's the scoop. A vector field is just going to be a function from Rn to Rn. Meaning the domain and the codomain have to have the same dimension. The dimension of the input vectors has to match the dimension of the output vectors. Which means we could be looking at functions from R to R, like in Calc 1, or we could be looking at functions from, say, R2 to R2, or R3 to R3, or in Dr. Verstal's sadistic mind, R8 to R8. We're going to be focusing mainly on R2 to R2 and R3 to R3. And so, example I want to look at, start things off, is going to be the function g of xy is equal to y comma negative x, which is a function that's going to take in vectors in R2, and it's going to spit back out vectors in R2. And our goal is going to be to graph what does this look like. Dr. Gerstel, thought you said we couldn't graph functions from R2 to R2. We can, we just have to be a little bit crafty about how we're going to graph these. And the way we're going to graph this function is going to be a little bit different than the way we graph functions back in, say, Standard 6. And that our goal in graphing is going to say at each point x comma y, we're going to graph the displacement vector corresponding to g of xy. So let's see what that means. So I'm going to make a little table over here to the side where we're going to look at a bunch of different inputs into the function and then see what the corresponding outputs are going to look like. So we're going to graph some look at some xy's as well as their corresponding g of xy's. 0, 1, 0, negative 1, and 0, 0 to start with. Lindsay, if we were to plug 1, comma 0 into the function g, what are we going to get as an output? Yeah, the output's going to be 0, negative 1, because this function swaps the x and y coordinates and then makes the new second coordinate negative. So 1, 0 gets swapped to become 0, 1, and then second coordinate becomes negative. So what that means is we're going to go to the point 1, comma 0 and draw a displacement vector pointing in the direction 0, negative 1. What would that displacement vector look like? If I were to say, starting at this point, draw a vector pointing in the same direction as 0, negative 1. Would that point up, down, left, right? Diagonally? Up?
Straight down.
It's going to point straight down 1 unit. So we're going to have an arrow that looks like this. Vector starting at 1, 0 and that is a displacement vector pointing in the direction of 0, -1. Sarah, what would g of -1, 0 be?
0, 1.
And 0, +1. So if I go to the vector, so if I go to the point -1, 0, which direction am I going to draw an arrow?
Straight up.
Towards 0, +1, which is going to be straight up in this case. And then similarly, if we plugged in 0, 1, we get an output of 1, 0. So I'm going to go to 0, 1, draw an arrow in the direction of 1, 0, which is to the right. At 0, -1, we're going to get an output of -1, 0. So that'll point to the left 1 unit. If I plugged in 0, 0 into the function, I get 0, 0 as an output. And Brianna, what would it look like if I were to draw a displacement vector starting at the origin corresponding to 0, 0?
Wouldn't go anywhere.
You wouldn't go anywhere. So what would I draw there?
Dot, I suppose.
Yeah, we're just going to draw a dot saying, at that point, it's just the output is the 0 vector, which doesn't have a direction, or any length to it, or a direction, really. So typically, when you're drawing a vector field, this is the sort of, or graphing a vector field, this is what you do. You look at your input, a bunch of different input vectors, see what do the corresponding output vectors look like, and then at each point corresponding to an input vector, we're going to draw an arrow that's a displacement vector corresponding to the output. I'm going to go ahead and draw a bunch more arrows just to kind of populate the plane. And in essence, this is kind of going to be what our vector field ends up looking like. And that's like, and you can find that by just plugging in more points just to see kind of what ends up happening. But you should get some image that looks something like this for our vector field. G of xy equals y negative x. At each point, theoretically, I've placed an arrow corresponding to what I would get if I plug that point into the function. Now, technically, you can't plug in every single point because there's infinitely many in R2. But when you're graphing these vector fields, you generally just draw enough arrows to kind of get the idea for what's going on in the picture. Anybody see like any sort of pattern in the arrows that's happening here? Yeah?
They're kind of making a whirlpool. They're all going clockwise.
Yeah, looks like there's some sort of idea of like clockwise circular motion going on here. That if we were to kind of, like if these were, for instance, water currents, and we were to plop a boat down in here, looks like it would sort of be traveling in sort of a clockwise circle. If I were to go here, it'd start off going this way, and then maybe go in this way, and then kind of loop around and do something like this. Potentially ending up right back where it started. And that notion of being able to take a vector field and kind of being able, graphing it and noticing patterns in the vector field is going to be something that's very important to us. And that it's going to allow us to kind of see motion somehow from a function going from R2 to R2 in this way. Any questions about this example before I move on to the next one? We're going to come back to this example here in a couple minutes and see and actually prove that there's circular motion going on here. But next up, I wanted to take a couple minutes and look at another example that is not in the packet. This is going to be a vector field from R3 to R3 that I think is a pretty cool one. Holly, can you do me a favor and hit the light switch back there? I want to show this one off. This one's a pretty cool one, in my opinion. By the way, here's the vector field we just found. Y negative x. What about this one? I would call this a vector field from R3 to R. No falling asleep, by the way. I would call this a vector field from R3 to R3 that's going to take in points on the surface of the Earth, on the surface of the sphere. And can anybody want to make a guess as to what these sort of arrows are representing here? What these sort of lines? Sarah? I think it's actually air currents, but it could just as easily have been ocean currents going on here. Yeah, but they're currents. It's like measuring air patterns and like airflow. If you were a particle on the wind here, you would be flowing sort of in this direction. And while normally vector fields aren't actually moving, usually they're static. This one is kind of demonstrating how a vector field can change something moving within it over time, corresponding to the wind currents. Anybody? So who do you think might be interested in a vector field like this? Who might be interested in knowing something about how wind patterns move on the surface of the Earth? Jackson?
I guess like other people.
Other people?
Maybe like the forecasters and stuff like that.
Okay. Yeah, weather people. Meteorologists would care very much about, how is the wind moving in order to be able to predict weather patterns. I don't know, if we have some sort of wind pattern like this, that's where everything's spiraling inwards. Rotate so I can get a better look at that. That could be say a hurricane or a tropical storm, or, since this looks like off the coast of Japan, a tsunami. Oh, no, actually that's not. Japan's way up here. This is the Philippines. So knowing about how vector fields can behave and change movements like this over time can be something that's really important and relevant to the real world. Any questions or comments about this air pattern example? Yeah, Brianna?
So if you wanted to map it over time, could you add another variable to your vector field, or would you have to be outside of the vector field formula?
You could add another variable, like x, y. You could have for instance, a g of x comma y comma t that spits out y comma negative x comma t, and see how something is moving over time. It's going to add extra dimension to your vector field. You could definitely do something like that. In that case, this would become a vector field from R4 to R4, and having this vector field in motion is kind of the best way, I think, how you would visualize something like that. Good question. Anything else? Okay, Holly, can you hit the lights again for me? Thanks. Now that you've seen a couple examples of vector fields, I'd like for you all to take a look at a couple yourselves. So what I want you to do next is to take a couple minutes and look at the next couple pages in the packet, specifically looking at a couple vector fields, one going from R3 to R3, h of xyz equals negative x, negative y, negative z. And also k of xy equals 0, comma, y squared. And what I'd like for you all to do is take a couple minutes and see if you can graph what do these vector fields look like if we try and visualize it. First one is going to give us a graph in R3, and the second is going to give us a graph in R2. It's going to take a couple minutes, and as always, you're welcome to talk to and work with your neighbors and see what you can find. First one's a little bit tricky because you have to graph three-dimensional arrows, but the arrows should all have something in common in how they behave. As always, if you feel stuck or confused, you're welcome to ask your neighbor or to flag me down. Keep in mind your graphs don't have to look perfect, but they should you should be able to see from looking at your graph like the general pattern of what do the arrows basically look like.
Oh, you're right.
You could add the so basically the displacement vector is going to start at this point, point in this direction. You could add the two to see where it would end up, and that would tell you where your arrow should end if you wanted to. That would be if you added sort of the starting point to the displacement vector. So like here, for instance, when we took like at at 0, 1. We plugged 0, 1 into here and got 1, comma 0. What that meant is we went to the point 0, 1 and then had an arrow pointing that looked the same as the position vector 1, 0, just starting here instead. So it would point 1 unit to the right, starting at 0, 1. That's you feel like you have graphs that you feel confident in, I encourage you to turn to someone sitting around you and see if they agree with you on what your vector field looks like. What would we have done if I had gotten to the last couple standards? Last couple standards would have been how do you integrate on a vector field. Ultimately, like that would lead us to something like if we're moving along in this circular space, like in a full circle, how much work have we done? Get into a little bit of physics. How much work is done in moving a boat half a circle around this space? And then last standard would have been looking at a slip theorem called Green's theorem. Would have basically related the integrating over a vector field to doing a double integral from what we did the last few standards.
Do you think that would be worth higher level math classes?
Not necessarily. Higher math classes that use them, like complex analysis uses like line integrals, I think, would like review those. Okay, so let's come back together and take a look at these. So, first vector field was took in a vector xyz and just spat out its negative. xyz gets mapped to negative x, negative y, negative z. Anyone like to share with me what their vector field ended up looking like? Specifically, what did all the arrows have in common? Oh.
All of them point to the center, and they all end at the center.
Yeah. Every single arrow in this vector field right here is going to point to the origin, no matter where you start. And this is due to the fact that at every single point, if you're spinning out the negative of that point, well, if we were to start at the point 1, 1, 1, for instance, and look at what would happen if we traveled -1, -1, -1 from that point, the end result would always be at the origin, no matter where we started. If we started at any point A, B, C, and then traveled in the direction of -A, -B, -C, we would end up at 0, 0, 0 at the origin. So this one, all of the arrows are going to be pointing inwards to end at the origin. I would actually call the origin a sink or an attractor in this case, which is something we might get to on Wednesday. How about this one? K of xy equals 0, y squared. What sorts of patterns ended up happening in this one? Ollie?
Mine look like they all pointed to perfect squares on top of the
They all form what?
Like they all pointed to like perfect squares.
Oh, they're pointing to thick coordinates that have a whose second coordinates is a square number. Yeah, if we're going to plug in integers, especially for x and y, the output is always going to have a y coordinate that is the square of the y-coordinate of whatever we plugged in. So if our inputs are integers for y here, they're going to be squares of integers here. So like if we were to plug in y equals 1, 2, or 3, y squared would be 1, 4, or 9. Yeah, that's certainly true. What direction did all of your arrows point, Holly?
Towards the positive y-axis.
Towards the positive y-axis. I agree. In other words, all of the arrows are going to be pointing upwards, due to the fact that the x-coordinate is all of our outputs is 0. So the output arrows aren't going to point to the left or right at all because the output x-coordinate is 0. And since the second coordinate is always non-negative, since y squared will be 0 if y equals 0, meaning we're going to get a bunch of points along the x-axis here. But as long as y is anything other than 0, the y-coordinate of our output will be positive, and so we'll get arrows pointing upwards. So for points that are close to the x-axis, we're going to get points that point upwards a little bit. But for points that get further and further away from the x-axis, the outputs are going to be more and more positive. Similarly down here, for points close by, they're only going to point up a little bit. But for points starting with very negative y-coordinates, when we plug them into our vector field, the output is going to have a very positive y-coordinate. Which would give us a sort of scenario like this happening. But in any case, as long as we're starting at a point that's not on the x-axis, we're going to get an arrow that's pointing straight upwards, corresponding to 0, y squared, having a 0 x-coordinate and a positive y-coordinate. Yeah, Emily?
How exactly do we graphics I would, and this one I would plot going towards the y-axis or the x-coordinate.
So they're not going to point towards the y-axis necessarily. When I say that, like, let's take a look at an example. Maybe I shouldn't have erased this here. I'm erasing it now. So Emily, can you give me an example of a point you tried plugging in as an input to this one? Okay, so if we looked at xy of 1, 1, and our output k of xy would be 0, 1, right? So if we go to the point 1, 1, let's say 1, 1 is, I don't know, about here. And to see at this point right here, where should our arrow point? The fact that our displacement vector is 0, 1 doesn't mean we need to point to the point 0, 1 in the xy plane. It means we need to draw an arrow that goes 0 units in the x direction and 1 unit in the positive y direction, and that's why it would always point just straight up. In order to point towards the y-axis in this scenario, we need to have a negative x component for k of xy in order to be able to point to the left at all. Does that make sense? It's basically the difference between, are we pointing to the point 0, 1, or are we just going to travel 0 units in the x and 1 unit in the y direction? And it turns out to be the latter whenever you're drawing these vector fields. It's a good question, though. I'm glad you asked. Anybody else? So, I think Brianna, I think you were the one who noticed in looking at this vector field, g of xy, that it looks like there's some circular motion going on. I would say, well, I erased it now, but in the second example, it looked like there was some general motion being towards the origin. And in this example, I would say there's a general sense of motion of moving upward, so to speak. So what we're going to do next is we're going to talk about how to make that idea of there seems to be motion in this direction, and we're going to make that notion a little bit more formal by talking about something called flow lines on a vector field. Get these out of here. And so we define this. We're going to define a flow line as being a specific type of function that when we graph it out is going to sort of give us, in this case, a circle, and in this case would give us a line moving upwards. It's going to be a path that shows what would happen if you were to be trapped, say, inside of the vector field. So first of all, let's define it as being a flow line of vector field F going from Rn to Rn is going to be a differentiable function which I'm going to call x of t, which will generally be a function that starts in R and ends up in Rn. Dr. Gerstle, in the packet, it says an interval from A to B. Yeah, I'm going to call it R to Rn, what I do on the board. And we need that path to satisfy that if we were to take x prime of t, meaning we were to differentiate each of the components of x of t, we would get the same thing as if we were to take f of x of t. And what this intuitively will tell us, if x prime of t equals f of x of t, is that the path matches up with movement in the vector field. So let's see if we can calculate what that might look like in this example here for g of xy equals y negative x. So g of xy here is a function going from R2 to R2. So what we need to find is going to be some path x that's going to go from R1 to R2 that satisfies this condition, that if we were to differentiate it, we would get the same thing as taking g of x of t. So let's do that. So first of all, I'm going to let x of t be equal to, let's say, g1 of t, comma, g2 of t. We have a function going from R to R2. It's going to be a function like this that takes in a single variable as input and spits out an output with two component functions as a function from R to R2. And let's see what conditions g1 of t, comma, g2 of t, what do those component functions have to satisfy to make this equation work out. So first of all, we know x prime of t is just going to be g1 prime of t, comma, g2 prime of t as a vector. We just differentiate each component, we'll get that. If we were to take g of x of t, that would be the same as taking g of little g1 of t, comma, little g2 of t. And what is that going to give us? If big G takes in a vector xy and always spits out y negative x, where it swapped the order of the two inputs and made the second one negative, if in this scenario we're plugging in two component functions, little g1 of t and little g2 of t, into our vector field, capital G, what is our vector field going to spit out? Yeah?
G2 of t, negative G1 of t.
I like it. G2 of t, comma, negative G1 of t. Corresponding to the fact that what capital G does is it swaps the order, makes the second thing negative. xy becomes y negative x. So G1 comma G2 becomes G2 comma negative G1. We're just swapping in G1 of t and G2 of t into x and y in this formula respectively. So what does that tell us? Well, that tells us if x prime of t is equal to big G of x of t, we need that these two vectors are the same, which is going to tell us that G1 prime of t has to equal G2 of t, and similarly, G2 prime of t is going to be the negative of G1 of t. In order for these two vectors to be equal, we need that their first components are equal, G1 prime equals G2, and their second components are equal. G2 prime equals the negative of G1. All right, who am I going to press with this one? Sarah, I'll ask this one. Can you think of any functions, any pairs of functions, that the derivative of the first is equal to the second one, and the derivative of the second one is the negative of the first? Totally okay to say I can't think of it.
Not off the top of my head, no.
Okay. Laurie,
Sine.
I think that would be kind of the classic, probably the simplest example is just the trig function, sine and cosine. So, for instance, you could let g1 of t be sine of t, and g2 of t could be cosine of t. Because if we did that, the derivative of g1 would equal g2, derivative of sine is cosine, and the derivative of g2 would be the negative of g1. The derivative of cosine is negative sine. And so this, the function x of t equals sine of t, comma, cosine of t, would be an example of a flow line of this vector field. Because this function right here is going to satisfy that if we were to differentiate each component of this function, we would get the same thing as if we plugged in this function, x of t, into our vector field. In either case, we'd end up with cosine of t, comma, negative sine of t. Any questions or comments? What would be another example of a flow line? In other words, what would be another pair of functions other than just plain old sine of t and cosine of t that would satisfy these two equations? I'll give you a hint. Think of very similar looking functions. Oh, we could have cosine and negative sine. Derivative of cosine is negative sine. Derivative of negative sine is the negative of negative cosine. And no, derivative of negative sine is the negative of cosine. That can be negatives there in that sentence. But yeah, that would be another example. You could also have something like g1 of t equals cosine, g2 of t equals negative sine. And then I'll give one more, just so we have it. Another one would be 2 sine of t and 2 cosine of t. If you take differential equations, which is a math class offered here at Hillsdale, hopefully going to be offered every spring from now on, you'll learn about how do you find all the solutions to a system of equations like this one, where the derivative of the first is second, derivative of the second is negative of the first. Differential equations, you learn how to find all solutions to systems like that. So what I'd like to do is I'd like to graph what does one of these paths look like, which is something we talked a little bit about back in Standard 6. So specifically, I'm going to look at the path x of t equals sine of t, comma, cosine of t. Just to see what is the graph of that, or sine of t, comma, cosine of t. Just to see what does the graph of that look like. First of all, Tim, if we were to plug in 0 for t in this equation, what would be our output point?
Sine of 0, cosine of 0, so 0, 1.
Mm-hmm. Yeah. When we plug in t equals 0, we'll get the point 0, comma 1. So we'll get a point up here. If we were to keep going, let's say if we were to look up to x of pi over 2, Avery, what would that give us?
1, 0.
Yep, that's going to give us 1, 0. Point down here. And in the meantime, it's going to trace out a circle in order to get from x of 0 to x of pi over 2. Mainly because sine squared plus cosine squared will always be 1. Alright, how about x of pi? Other way around. Yeah, it's going to be 0, comma, negative 1. And so if we continue along that path towards 0, negative 1, we're going to keep getting this circle is going to keep moving this way. If we were to keep going, we would get x of 3 pi over 2, which I'll just tell you is going to be negative 1, 0. It's going to loop back around this way. And finally, if we were to go all the way out to 2 pi, we would end up back where we started at 0, comma 1. And so what this curve traces out, what this path, x of t, traces out, is going to be a circle, in fact, a unit circle, traversed in a clockwise manner. Which, Brianna, I think is how you described the behavior of this earlier. We're getting a clockwise circle. And fun fact, any of these flow lines that we're going to get is going to look like a circle. If we were to do 2 sine of t, 2 cosine of t, it's also going to trace out a circle just of a different radius. So it turns out any of these flow lines, when you graph them out, is always going to give you sort of a path that matches up with the flow of the vector field. It's a path that kind of follows the arrows, so to speak, from wherever you might start. Last thing before I let you go. That's not what I said. If you were to go into CalcPlot 3D, you can actually get them. You can actually get it to graph the flow lines for you. Let the projector warm up for a second here. So let's let the projector warm up for a second. going to give this 30 more seconds. Here we go. If you go into CalcPlot 3D, you can actually click on the graph, and it'll show you. The. It's a little hard to see because they make it rainbow colored for some reason. It'll actually show you the different flow lines, where all the flow lines are going to be circles, corresponding to the fact that if you were to start anywhere in this vector field and to follow the arrows, you're going to be going in a circular pattern. If you want, you can even play around with this. Go and make vector fields in CalcPlot 3D, click on various points. It'll tell you, here's what the flow line looks like that goes through that point. And with that, it's going to do it for today. Hope you all have a good rest of your day. I will see you all on Wednesday. On Wednesday, we will finish Standard 17 by talking a little more about flow lines, and then talking about, since this is Hillsdale after all, we'll talk about conservative vector fields.
I was wondering if I have all the standards done but I'm not final exam, should I still come in and take the final exam?
Only if you really want to,
Okay.
because it won't do you any good at that point.
Okay, so I just don't need to come if I have it done.
In that case, I would just say, if you could email me ahead of time just to let me know you're not coming, just so I'm not like looking like Dale, like, oh my gosh, I forgot to sleep through the exam.
Okay.
But yeah, no, that would be perfectly fine in that scenario. No problem. Yes, I passed it back on Wednesday, so it's in my office. I was gonna say, if you want to wait till Wednesday, I'm gonna pass back everything I have on Wednesday, including the quiz you missed. But yeah, I have it in my office. I do have that graded. It's just been sitting in my office.
I can wait. I was just, yeah. All right. Thank you.
No problem. Have a good one.
You too.